Okay, kids, so based on what we did yesterday in class with the Desmos, hopefully you got the basic idea of this, but just in case you need it all written out for you, that's what we're going to do here. So transformations, day 2, what it means for a translation. Remember, that moves it left or right. So how does it look in the function? Well, if it's inside the function, it's going to move it left or right, and hopefully you saw yesterday that plus actually means it moves to the left, and minus means it moves to the right. So an example of that would be like if you had f of x as x squared as the parent function, then the transformation would be like g of x equals x plus 2 squared. And that would be 2 units to the left, okay? So keeping this same one as the parent function for each of these, if it was minus, if that would be like x minus 3 squared actually means that it moves to the right 3. Now, if the number's added or subtracted outside the function, that's when it moves up or down. And that one, it makes sense. Plus means move up and minus means move down. So if you had like g of x equals x squared plus 7, that would move that parabola up 7. I'll change it up here. And h of x here, if it was x squared minus 6, that would move that parabola down 6. Okay, so you got to know, adding and subtracting moves it a translation, and whether it's left, right, up, or down, depending on how it's written. The other ones are reflections, and whether it reflects on the x or the y depends on where the negative is. So if the negative is on the outside, it's over the x-axis. So let's make our parent function on this one be the absolute value of x. So if we were going to flip that over the x-axis, then that would be like negative absolute value of x. If you were going to flip it over the y-axis, for absolute value, nothing would change really because it's still a positive, but the negative would be on the inside. You could write it like that, but it would still look the same. And then the other ones that we saw, that when you multiply by a number inside or outside the function, it changes the graph, it stretches or shrinks it. And this one is the most confusing rule. But if it's on the outside, outside means vertical, inside means horizontal, and it's all about whether the number is bigger than 1 or like a fraction between 0 and 1. So if it's going to stretch it vertically, again, I'm just going to go back to x squared. If we're going to stretch it vertically, that would be like y equals 2x squared. The 2's on the outside, and it's stretching it by a factor of 2. If it's going to compress it vertically, or sometimes people call it a shrink, that's if it's a fraction. So like if it was y equals 1/3 x squared, that's going to shrink it vertically. And horizontally, it's the opposite in terms of whether it's a compression or a stretch or an expansion. If the number's bigger than 1, it's actually a compression. So like if it was, let's say, parenthesis 2x squared. See, the 2's on the inside, so it's horizontal, but because it's bigger than 1, it's actually compressing it horizontally. And if it's going to expand it, it's going to be a fraction. So that's going to be like parenthesis 1/2 x squared. Okay, and we'll work on that more. Okay, so let's practice how this can help us graphing. Okay, so it says, describe the translation in this and then graph the function. So describe it is what's happening. So looking at this plus 1, it's on the inside. So hopefully you said that this is going to move left 1. So I want to show you how you can use this to help you. Okay, so I'm going to graph the parent function first. The parent function is y equals x squared. You don't have to do this every time, but I just want to do it at first so you can kind of see what's happening, that it's really just sliding it over like what we did in class yesterday or today. I don't know, depending on what day you watch this. So I'm going to graph it in black, all right? And this is the parent function that I want you to know. You need to know this basic graph, hopefully without having to make an XY chart every time. But I know when I plug in 0, I get 0. I know when I plug in 1, I get 1. And actually when I plug in plus or minus 1, I get 1. And when I plug in 2, I get 4. And negative 2, I get 4, because 2 squared is 4. Here's a really cool pattern with parabolas, that the distance between the points go up like in an odd fashion. So like the distance between, I'm going to use different colors here. From here to here, I go over 1, up 1, it's 1. If I go over again, that's a distance of 3. It goes 1, 3. The next one would be up 5 and then up 7. So it's growing at a fast rate. And so that's kind of the parent function that I want you to know. Okay? Make an XY chart if you need to. What we're going to do is we're going to move this left 1 unit. So like with the magic of my smartboard here, I could think about taking this and I'm just going to slide it over. What I want you to do is I'm going to graph this in a different color, or maybe you just don't even graph this or make a new one. But I'm going to do the same thing. If I know the shape, I just slide it to the left 1, and I do the same pattern where I go over 1 and up 1 on each side. And then from this point, I'm going to go over again and up 3 because it hasn't changed shapes. It's just moved. And just a little practice here, the domain of this would be all real numbers. The range of this would be the lowest y value is 0 to infinity, which is the same as the parent function because we just slid it over. So what about this one? It says describe the reflection. Oh, it tells us it's a reflection. On the outside, what does that mean? Well, this means that it has flipped or reflected over the x-axis. So again, parent graph on this one, you should know that the parent graph, y equals absolute value of x, starts at 0, 0, and it's just up through the middle of that, right? Like a slope of 1 on this side, and this side is the exact same, or think about like a slope of -1, like this. If you know that, and you know it's just flipped over the x-axis, you don't have to make an xy chart, right? You just flip it over, and you just make all the y's now be negative. So it's the same graph, hasn't changed shapes, I've just flipped it over. But think about what the domain and range of this would be. Domain, still all real numbers. The range, 0 is now the highest number on this, so this would be -infinity up to 0. Okay? But hopefully this is helping with the graphing. When there's a dilation, if you're not sure what's happening on this, make an XY chart. It doesn't hurt to do that. I'm going to show you how to do it without it, but I'm going to make the XY chart too, okay? This one, the shape is changing, okay? So this one's on the outside, so this is a vertical, and it's less than 1, so that's a vertical compression or a vertical shrink. Some books call it that. So again, if I graph the regular function, I'm going to do that first just so you can see it. You don't have to do this, but just to show you what happens, how the shape is changing. Like this one's going like this, right? If you aren't sure what to pick or how to graph it, pick points, right? So pick 0. 0 times 1/2 is still 0. But if I pick 1 now, I'm only going to go 1/2 instead of 1. If I pick 2, I'm going to go 1. If I pick -1, I'm going to get the same values, right? Because it's absolute value, -2. So look what happens. 0, 0. Now, normally I go over 1, up 1. But now I have to go over 2 before I can go over up 1. Or at 1, it's only at 1/2, right? So what's happening here, if you think about a vertical compression, it's like if you took a big book and you push down on that black graph, it's going to spread it out. And that's what's happening. It's changing the shape of it. Has the domain and range changed any from the parent graph? No, because we didn't actually move it any. We just pushed it down. The domain is still all real numbers, and the range, even though you push it down, it's never going to go negative. So it's going to be 0 to infinity. And we'll practice this more in class.